We're always thinking, right? Updating our beliefs, trying to figure things out. For those of you always asking why, how do we actually measure that change in understanding?
That's a great question. How do you quantify the gap, between what you think is going on and what's really going on?
Exactly. Is there a number for that?
There is, and it's fundamental to so much today, especially AI and statistics. We're going to explore the Kullback-Leibler divergence. You'll usually hear it called KL divergence.
KL divergence. Okay. Sometimes relative entropy too, I think.
That's right, relative entropy or I-divergence. Different names, same core idea.
So our mission today is to really unpack this. What is KL divergence? And how does it measure the difference between, say, the true state of the world, let's call it P,
The true probability distribution, P, yes.
and our model or approximation of it, Q? Why is this one measure so important?
Well, fundamentally, the KL divergence, written as parallel Q, gives you a precise number representing that difference. And crucially, it's always zero or positive.
Zero means?
Zero means your model Q perfectly matches reality P. No divergence. The distributions are identical.
And positive means there is a gap. The bigger the number, the bigger the gap.
Exactly. A larger value means Q is a poorer approximation of P. It quantifies how wrong Q is in a specific information theoretic sense.
Okay, so if P is reality and Q is my maybe flawed model, what does that number mean? Is it just a penalty score?
It's more than just a score. It has a really neat interpretation. Think of it as the expected excess surprisal.
Excess surprisal.
Yeah, imagine you're expecting things based on your model Q, but the world actually operates according to P. The KL divergence measures, on average, how much more surprised you'll be by events than you would have been if you'd used the correct model P from the start.
That connects nicely to the coding idea, right? Like sending messages.
Precisely. If you design a data compression code based on your assumed distribution Q, but the data actually comes from P, well, your code won't be optimal.
You'll need more space, more bits to encode the real data.
You got it. D-text parallel Q is the average number of extra bits per message you'll need because you used the wrong code, the one optimized for Q, instead of the truly optimal code based on P. It's the cost, the excess entropy.
Okay, that's a very tangible way to think about the cost of being wrong. Now, you called it a divergence. Is it like distance? If I measure the distance from point A to point B, it's the same as B to A. Does that hold here?
That's a critical point. No, it doesn't. KL divergence is a statistical distance, or more accurately, a divergence, but it's not a metric in the strict mathematical sense.
Why not?
Two main reasons. First, and this is huge, it's not symmetric. The KL divergence from P to Q, text key parallel Q, is generally not the same as the divergence from Q to P, text Q to Q.
So the distance depends on your starting point. Measuring the cost of using model Q when reality is P is different from measuring the cost of using model P when reality is Q.
Absolutely. The perspective matters immensely. And second, it doesn't obey the triangle inequality. A to C isn't always less than or equal to A to B plus B to C.
That feels weird for a distance measure. Why use something that breaks those fundamental rules?
Because what it does capture is incredibly useful, specifically information loss or gain. While metrics generalize simple linear distance, divergences, like KL, are more akin to generalizing square distance. This asymmetry is actually part of its power.
How so?
Think about Bayesian inference. You start with a prior belief, Q, you get some data, and you update to a posterior belief, P.
Okay.
The KL divergence, parallel Q, KRDL, measures the information gain in moving from your prior Q to your posterior P. It quantifies how much you learned, how much uncertainty was reduced by the data.
So the asymmetry makes sense there. The information gained by updating from Q to P isn't the same concept as, well, whatever going backwards would mean.
Exactly. And this idea of extra bits or inefficiency connects directly to things like cross-entropy, which is everywhere in machine learning.
Right. Cross-entropy loss functions are used to train models. How does KL fit in?
Cross-entropy between P and Q is essentially the entropy of P plus the KL divergence DKLO Q. That KL term is literally the extra average bits needed because the model's predictions, Q, don't perfectly match the true data distribution, P. Minimizing cross-entropy means minimizing this divergence.
So we're minimizing the cost of being wrong when training AI models.
Precisely. And this isn't just theoretical. Look at modern AI evaluation. There's a metric called MAUVE.
MAUVE?
Yes, it uses KL divergences in a clever way to compare the statistical properties of text generated by an AI, like a large language model, against text written by humans. It measures the gap between the two distributions.
So KL divergence is really this fundamental yardstick for measuring how well our models, our beliefs align with reality, from basic information theory to cutting-edge AI evaluation.
It truly is foundational. And speaking of support, this deep dive is sponsored by Embersilk.com. You're looking into AI education or integrating AI, Embersilk is the answer for all your needs.
Embersilk.com, check them out. So before we wrap up, any final thought to leave us cheering on?
Well, there's a fascinating connection to physics. If you take the KL divergence and multiply it by the ambient temperature,
Okay.
it actually measures something called thermodynamic availability. It relates the information lost when using an approximation Q instead of the true P to the physical concept of energy that's no longer available to do useful work.
Wow. So information loss is tied to energy loss.
In a very real physical sense, it shows just how deep these concepts run.
That's definitely something to think about. Thank you for this illuminating dive into KL divergence.
My pleasure. Thanks for having me.
And for everyone listening, if you found this valuable, please subscribe to the deep dive and do give us a 5-star review. It genuinely helps us reach more curious minds.